So let's get started. So this is the second part of instruction scheduling. So what's instruction scheduling? Why we are doing this? Because modern microprocessors are basically not executing one instruction after another. They do a lot of other interesting things. One thing they do, they have pipeline stages. So what that means is multiple instructions can be active at different stages of the pipeline at a given time. So at a given time there are multiple things running. And also different instructions might take different amount of time in this pipeline. And on top of that, we might have multiple execution pipelines. So in every clock cycle, you can issue multiple instructions, so you have parallel execution. So the thing is, if you have two instructions that produce a value when others uses, if the value is not available when it's trying to use it, hardware basically stalls the instructions in modern superscalers. So in some machines you can't even schedule it. You have to actually explicitly insert no up instructions because the data wouldn't be there. So there will be all this stall. So what we are trying to do is in instruction scheduling we want to reorder the instructions so we can maximize the instruction throughput. So what that means, we want to get maximum amount of instructions executed. Both if you have parallelism, we won't have many things happening in parallel. So all the units has to at least have something going all the time. And we want to really minimize the pipeline stalls. We don't want people just waiting, doing nothing in there, even after we schedule. So this is the essence of that. So three things we have to worry about: data dependence, resource, and control dependencies. These little bit of review, so you don't have to. So data dependency between instructions means two variables access the same data. Two accesses access the same data. There are three kinds of accesses. True dependence, which is actually real data. Basically, somebody writes something and I have to wait from that. There are two other types of dependencies that are just artifacts because we can keep different variables at the same location. So it's called anti and output dependencies. That means you are going to rewrite the data anyways, but I am supposed to use it, so you have to wait till I am finished using before you can reuse that space. So those things you can actually eliminate by giving you different space. You don't have to wait for that space. You get a different space in there. But output dependence means two guys are trying to write, and I want to make sure the last guy is the one who writes last because it has to survive. And here, if you are smart, you can say, wait a minute, there are two guys writing, nobody's reading in the middle. Why is the first guy actually writing if nobody's using it? So you can do a lot of things, eliminate some of these things in some sense. And the key thing is we can't just arbitrarily reorder instructions. We have to make sure if we are reorder, we basically satisfy these dependencies. And computing dependencies, if it registers, it's easy. Same register, dependent. Memory can get complicated and can get arbitrarily complicated. We don't touch it in here, but still right now it's active research topic. If you look at the Java program, if you look at two variables, how can you say whether they are not referring to the same location? It's a same method, or basically same object. How do you say that? That's a hard issue. And there's still a lot of work going on in that kind of things. It's called a polytalious analysis. And what we do is we represent these dependencies using a DAG. Each instruction is a node, and each edge says, okay, the results of that instruction needed in the sink of the edge. And we put a number that says, okay, in order for the second instruction not stall, it has to start at least this many cycles after the first one. So first instruction get issued, and in here 1 to 4 that says after first instruction, the fourth at least have to have two instructions in the middle, so it won't stall. So if you do it earlier, it will go to stall. So this is the kind of representation we have. And the other type of constraint is resource constraints. Things like superscalers, you have multiple parallel units, and you need to make sure that all those units are kept busy, but there's also units are limited. So if you assume there are more than what you have, you might not get a good schedule. And I'm going fast because I went through last time too. Okay, so you should have seen this. This is the second time. So one example is, assume you have two units. One say every register operation goes to unit A, any memory operation goes to unit B. Okay, how do you run that? So what happens is the way to do that is it's almost bin packing. So assume you have these bins, you have these pipelines, each pipeline. And you have some instructions that are requirement of the pipeline, and you can figure out what's the furthest down you can put, and basically keep running. So if you know how to play Tetris, this is exactly you can do. So here's this the pipeline. So ALU operations, it could be different size like a Tetris piece, depending on, assume if it is 2 cycles, it look like a piece of 2. If it in memory pipeline, it's actually like a Tetris piece. So basically you have to move the Tetris pieces and fix it the best way you can. So the way you do it is I talked about list scheduling. List scheduling, basically you do a topological sort of this DAG. So what that means is all the dependents are basically things that are dependent are not scheduled out of order in this topological set. And then what you have is, if there's nothing dependent, if the instruction has no dependency or everything that's dependent is already scheduled, it's ready. So that means you can schedule it, there's no problem with that, and then you keep scheduling that, and basically you have to pick things out of the ready list and schedule. The key thing is, when you have ready list, you have multiple things. The way you pick things out of the ready list can make a big difference. If you pick the wrong thing, what happens is you can get it as schedule, but later on you might not have anything to schedule, and you might stall at the end. So there are a lot of kind of heuristics people come up with to pick up from the ready list, because if you want to do optimal solution, it's NP complete problem. So you can try to do optimal, but you will never get there. So basically you do that. So here's an example I have been working through. So I give some delays in here, and so the 2 methods we are doing is to pick is look at the distance from the leaf node. So the thing is, if you have a path, if you have multiple chain, that means the chain put dependencies. So the longest chain is probably the one that's going to really restrict amount of time that that process is going to take. So you look at the chain. If you are very high up on the chain, you better get that done fast, so more and more things can happen. So you calculate the depth in that chain, that is the D number, and if you get a tie of the D number, to do a tie break, you figure out the fan out. Fan out means if I schedule, how many more instructions will be joining the ready list. So that means things that has a lot more dependencies better get scheduled fast. And those are intuitive things. There might be a lot of other things that you can think of. And as somebody last time said, how about memory instructions? You should schedule them faster, because the memory reads always lead to use of the data. Yeah, that's a good. I mean, people can play with these heuristics. So in here, at the beginning, you have ready list of 1, 3, 4, and 6. And then now you do this Tetris game. The 1 is basically just 1 block. There's no dependency in here, just schedule that in there. And then a minute you schedule 1, now 2 becomes ready, you can add that in there. And 2 also has the highest depth in there, so you pick up 2. And 2 is depending on 1. And now 2 is this piece. So you have to actually put it after 1, because there's a dependency. So you can actually lay it out there. So it's not really Tetris, you can actually move things inside out. And then you pick up 6. 6 is ALU operation, there's no memory, so you move 6 there. And then this point you can put 7 in there. So you can pick up 4. The interesting thing is 4 is a memory operation, and it's not depending on anything. Now it can actually move in front of 2, because we had this empty space in there. You can shove it. So it's a little bit different from just bin packing, because you can order it anywhere in this thing. So you just find the earliest space you can shove it in that still doesn't violate dependence, and then do that. And 5 you add it to the list, and then you pick 7. 7 depends on 6 and 2, and so 7 has to go here. And then that gets 8 and 9 into the list. 3 has no dependencies, it can go anywhere. 5 depends on 4, and then 5 goes here. And then 8 depends on 7, so 8 goes here. And 9 depends on 7, 9 goes here. And then voila, you got your schedule. So what happens is now, this is the machine can execute in this order. So you have to, since superscaler will figure it out, you have to issue instruction probably 1, 4, 6, 2, 3, 5, 7, 8, 9 or something like that. Order the instruction in that order, do that, and then you'll get this very tight schedule in there. So this is what you have to do in here. In scheduling for multiple units. So there could be many different types of resources. Sometimes this can get arbitrarily complicated, because depending on different resources, it's not static. So in there, so this scheduling problem can get very complicated, but a very simplistic form of doing is what I just described. So the next thing is control dependencies. You have to, each basic block right now is doing scheduling basic block, but basic blocks are small. And what you want to do is trying to schedule across basic blocks. So we need to handle control dependencies. So there's a technique called trace scheduling people use, which is basically, instead of, the idea is most of the control dependencies has a branch that takes a lot more time than the other branch. It's like, for example, things like error condition will probably never happen. You want to deal with the other branch, and you optimize for that. And you can combine multiple basic blocks into the trace and deal with off-trace stuff, which can be slow because it doesn't happen that often. And you basically do cleanup code off-trace. So if assume you have a program like that, and you do some analysis, so like either static analysis or profile feedback, you run the program while and figure out where these branches normally go, and figure out, okay, this is the normal executed path. And you said, aha. I will basically take that rest out of that, align that path together, and then treat it as one gigantic block. But the problem here is still there are things going out and coming into the block, and that still makes scheduling hard because you can't just avoid them. So one technique is to create a block that has a single entry multiple exit, because then things become much easier because there's no things coming back, there's no control coming back into the blocks. Only thing is you're going out. So the way you can do that is you can replicate the rest, all the exits. So it's the same code replicated in the exit. So what happens is in this block, there's single entry from the top, and there are 3 exits. Exit out of A, exit out of E, exit out of H, that normal exits. And now what is you get a lot more freedom to basically move instructions all over the place. Okay, that's where we end up last time. So loops. So the thing about loops is most programs, 90% of the time or 99% of the times are spent in loops. Okay, if you think about it, something like a Pentium running at 3 GHz has such a need for instruction, such appetite for instruction. So if you have to feed new instructions one at a time, you'll never be able to, you'll run out of the entire disk in few minutes. If you think about running at 3 GHz, one instruction at a time, just calculate how much instruction is needed to kind of keep this piece fed. So how do you deal with that? Because you can't put instructions at that speed. The only way you can deal with that is most of the time is trying the same instructions again and again and again in a loop. And that's how these machines actually run very fast. So because of that, performance in many cases is in loops. So running loops fast is very important. And loop bodies are small, so it's optimizing that is not that complicated because you can find these very nice tight things. But it's disproportionately execution time is in there. And so because of that, most compilers do something very different for loops than it do for rest of it. So it's try to go and actually do something very interesting, nice for the loops. So I want to give you an example. And again, a simple machine I will use. Assume one load store unit and one arithmetic, one that actually do the only do ALU to ALU register operation. And one actually do the load store operations. When we used to do a class in RISC, this is a very nice distinction because load store is very different from register operation. They have a different set of instructions. In x86, it's just one big jumble. So I am trying to a little bit abstract out to give you a good handle of that. But as you go to the architecture, there's no nice separation saying I have a load store unit that has separate load store instructions versus memory unit that ALU unit that has ALU instructions. These are combined. So it's not that nice, but at least to get the concept, I'll do the simplification. So here's a simple source code. I'm basically multiplying the array by a constant, each element. So some assembly code is not, so can you understand what this assembly code does? So what I did was, from RDI, so the first move instruction means add both RDI and RAX together, use that as address to go get the data and move to R10. So what that means is the base is stored in RDI for AI. And RAX is basically the index, basically I keep adding. And then I do the multiplication from B R11 stores B and into A, and then I store that register back into that location. Okay, so those are 3 instructions. And then obviously, what I did was, here's the interesting thing. Why did I did a subtract instead of add? So I'm actually subtracting RX. I'm not actually running the loop this way. Yeah, I'm counting down. Why?
Say do an instruction at the top because there's a special, because I think you're using BG, so there's a special instruction that just checks to 0.
Yeah, so B0, because the thing is, if I'm counting up, I actually have to do a comparison again when you reach the max. If I'm counting down, when I hit 0, I'm done. So I don't have to do compare instruction. So I just avoid the compare instruction by doing countdown. So do you get that? So here are the kind of things you kind of try to play with to get one instruction away. So here's my things, because you have to first do the move before you do the multiplication, because you have to get this data, and multiplication has to finish before you actually do the move back in there. I have a delay 0 because this move needs RAX, and this upgrades RAX. So I can't start doing this subtraction before I issue this instruction. So at least they have to happen at the same time. Because I'm using that, I'm updating that one again. Because otherwise, if you do the other order, I would have updated it before I actually used it. So it has to at least happen in the same order. So that's why I put a delay 0 in here. And then after doing subtraction, you have to wait till this finish to actually do the branch. Fair enough? Okay, so this is the loop. So if you run this, so first you do the move, it follows by the multiplication, it says 3 cycles, and do the subtraction, and then when you start subtraction, you can do this next move, which followed by the branch. So this is basically what you can actually best you could assume you can get. I'm not dealing with any kind of resources or anything like that. I'm just looking at the pipeline stages you have to do. Okay, is this clear? How this goes about doing that. So okay, yeah, this is good. It doesn't give you that much. This is basically what the normal schedule would do. So then I'm going to talk to you about 3 different techniques that you can do around optimizing loops. First thing is a really simple one. Just unroll loop bodies, because what happens is loop body has a small basic block. By unrolling it, you might be able to get a few more basic blocks one after another. And also if you unroll it properly, so you don't need to have exit at the end of it, because what you do is you make sure you don't get into that body unless you have enough iterations. So what that means is you actually have to have a main body, unroll body, and also a loop after ends to run that. So assume you are running 7 iterations and you want to unroll twice. So what you want to do is run the main body 2 iterations, 4, 6, and the last body to run 1 more iteration. So because of that, in the middle you don't have to have exit conditions or anything like that. So the minute you go into the main body, you know you run into to the end, so you can move a lot of things around. That makes it clear how you unroll. Okay, I don't have a piece of code. If it is not clear, I can actually write in the board. And nice thing is it creates a much larger basic block, and you can eliminate this bound check. The issues of that too. If you keep unrolling too much, you create a much larger program. Other thing is, as I said, I have to have 2 different bodies in here. So I have to assume I am unrolling 64 times. So first I will do is for I equals, we'll say I had 0 to n in here. 0 to n divided by 64, step 64. Something like that. Okay, I'm writing on a weird syntax, but this is basically flow. And then what I had to do is another loop for I equals I, which is last iteration here, to n. This is less than 64, because this will up to the flow it will run, and then you run to 64. So problem is, if most of the time you only have we'll say 25 iterations or 30 iterations, you are going to try to do the first loop, nothing will happen, not a single iteration, and go to the second loop again and again and again. So you'll do extra check basically. So if so, this useful, at least you have 64 iterations to run, because otherwise that body is just never get executed. And also, if you do it, most of the time when you're starting a loop, there might be some startup cost and end cost in scheduling in there. So here's a loop. So what I want to do is I just unroll it one more, unroll it twice, and this is what I get. Okay. So only thing I did was I cut and pasted the loop body twice, and I eliminated the branch condition basically. And of course, I am guaranteeing that when you went in there, at least we'll have 2 iterations to run. So I am guaranteeing that I'm not showing that in here. So here, we didn't get that much. What we did was we eliminated one looped exit test. So I went from 9 cycles per iterations to 8 cycles per iteration. A big deal. But what this says is, by doing that, now we have a much larger piece of code. If we can do few additional things, you can actually do much better. So let's look at what we can do. So what happens is, a lot of times there are these registers we use to keep temporaries. They are stopping us from doing anything useful. Because in the middle, I am using both of them, I am using a register, same register, to keep a temporary value. And now since it's the same register, I can't move anything around. So here, what happens is, R10 is used twice. The first group use R10. You load something into R10, you multiply and store in there. And I use R10 again. So obviously you can't move them around because these intermix these instructions because of R10 is the same. So one thing I can do is basically make it different. I move to RCX. So I use a different register for that. Okay. Still, by doing that, you can't get too many things because still I can't do. I still have a bunch of dependencies in here. Still, the dependencies haven't changed. So one thing you can do is trying to eliminate unnecessary dependencies. Can anybody suggest some interesting ways to eliminate unnecessary dependencies in here? So let's look at the program. Okay. How can I get rid of some of the dependencies? Don't look for the next page, it's there. Okay. How can I get rid of dependencies? What can I do?
Could you keep 2 counters and subtract 8 from each of them?
Exactly. So that's the thing that I'm going to do. Instead of because my dependence chain is basically this: I have I, and then until I do I plus 1, I can't do the I plus 4, I can't do the next one. And I can't do any other computation until I get the I plus 4 done. So I mean that keeps your 2 very tight together in there. And if I keep 2 different things, 2 different variables, I'm much better in there. What else can I do? What other type of things can you do? There's nothing in here though. But any suggestions? I think a lot of things you did in the last segment, data flow optimizations can apply here. Because between iterations, you might have a lot of common sub-expressions that happen. Because what happens is each body might do some kind of address calculation. And the next time, I've actually almost done that here. Because what I have done is I got the address calculation. Basically, I'm just adding value to the address. I'm not doing the full address calculation in here. So sometimes you might not have done things like code motion and common sub-expression elimination because it creates more live ranges. You have to keep more values around. But now you are merging the loop together. You might be able to do the address calculation once and bring the operations very close to each other. So you can reduce the live range. Because if you have 2 things, basically you create a lot of live ranges across because you're doing an address calculation, keeping it in a register and then moving it across. But now if I can have the ability to overlap each other, I can do the address calculation once and use it twice and reduce the live ranges. So the thing about this is the compilers, we love to do optimizations in these nice phases. But at the end of the day, it's a big, gigantic mess because, okay, most optimizations are not obviously always good. It reduces something, increases other. And then it's useful if the next time around you can actually go get rid of the other things. So that's exactly. So if you do common sub-expression elimination, if you understand that and 2 things use the same expression, eliminate that, reduce it 1, then you have to keep that expression value across. So if that distance is fast, you actually increase a large live range. You might have to go do some register spill because now you need more live ranges. But on the other hand, the minute you can do that as well as move the instruction next to each other, it might be really good. So in reality, that's why compilers get very complicated. Because even though you can say like all these passes are independent, a lot of times the decision to do something is a very dependent decision. And things get complicated. So here you don't have that much thing. So what I'm going to do is exactly what he pointed out. Basically increment or subtract 8 out of that both. So I keep 2 different variables. So now you see I increase the live range because I added 1 more variable in there. Now instead of keeping 1, I have to keep 2 variables. I hope, luckily here I have enough registers I can do that. The minute I do that, I can go into a much tighter schedule. Okay, this is basically, I mean, you can go and figure out how I packed it, but I packed it in a way that a lot of these things can happen like in a very tight form. Okay, so
is this loop now, so now in order to unroll this loop, you mean that it executes at least twice? Or does this also mean that it executes an even number of times?
So what happens is if I am actually doing this really, I will actually have 2 loops. I will have the loop twice or 4 time unroll loop that actually goes only enters when at least there's 4 iterations, and there will be another original loop left at the bottom to do the last few iterations. So I had to do that. I didn't show it that code here. Because what matters is the main loop, because that's going to run millions of times. The other guy will run a few times, so I don't care about that. The key thing is to get the one, because the reason these programs run for a long time, because there's a loop probably run millions and billions of times, again and again and again. If you get that millions of time running fast, you're set. And the last 10 iterations, who cares? So I'm not showing the full piece of code here. I'm just showing that main thing. So the next thing I want to get at is this interesting technique called software pipelining. I am not going to explain it fully. I will give you the kind of the intuition to show you what happens. So software pipelining says, why can't you overlap multiple iterations so that all the slots, because if you look at one iteration, as you saw, it was like a very sparse. The lot of slots were empty. Why can't you like overlap multiple iterations so nothing is empty? So every cycle, many things are going to happen. And then what happens is when you do that, at some point you can find a steady state window that says, if you keep repeating that, basically you can get the entire computation. Let me actually show you the example. I mean, this is much easier to execute. So here's the normal schedule that we had. Okay, so you can't make it any compact in this one. So one thing, but on the other hand, nice thing about this schedule is there's no dependence between iterations. So what you can do is you can pick up another copy and figure out where you can put that copy. So you can put that copy a little bit off. So I can run the second iteration kind of overlapping. I move 2 in there and put it in there. Okay, and then what I can do is I can pick up another copy and move it 2 and put it in there. Okay, then I can pick another copy, move it 2, put it in there, another copy, move it 2, put it in there, keep doing that. Okay, so now what happens is multiple things have overlap with every available space. I just moved another copy and just plopped it in, another copy, plopped it in here. I basically have to have 2 off because in each line I actually had using 2 slots in there basically. And then what? Okay, last one. So I keep moving that. So the interesting thing is this is great. Now does that mean you're going to unroll 8 times? And of course you can do by unrolling now 6 times and basically moving things around. But then what happens is all the time unroll. What happens is if I keep running this, there'll be a part at the beginning where there's nothing much happen. And there's a part in the middle, almost every iteration, every cycle, a lot of things happen. And then part at the end again you have to taper off the toil. So what happens is you have nothing much happen, lot of work, nothing much happen. So if you keep doing that, at least a large chunk of time is basically at the beginning and end. So we don't want to do that. We want to do the beginning once and run the middle many times and the end once instead of doing that. So how do you do that? So that's what the software pipeline does. Software pipeline does is, if you look at this block, okay, so what it does, it says is, it's doing these 2 instructions of, So actually it's doing 2 instructions of the first iteration. Okay. If you look at this, what happens is every instruction is in here of the computation, but at a different iteration. Okay, the computation has 2 moves, 3 mulls, 2 subtractions, and also another. It's moved and graded. So what it has is those mulls are here. These 3 mulls, these 2, these 1 here. And these first 2 moves are here. So if you look at, I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I guess. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, I guess. 10 instructions. I have my 10 instructions in there. So you do all the instructions at different iterations, and it's pretty compact, because in 2 cycles you can do everything. And then if you keep repeating that, so what happens is the first iteration you do some instructions, and it's at a given time the different iterations. So in a steady state, you're doing a lot of work for multiple iterations. So what you have to do is you take this unit in there. And so what happens is now there are 4 iterations overlapped. The thing about software pipeline, you need a lot of registers, because now you created a huge amount of live ranges. So that means you need things like value of R11 doesn't change, but RAX now had to keep out 4 different iterations RAX. So I had to have 4 different values of RAX that each get incremented. Now instead of 4, it's 16 every time. And I need to keep 4 registers for R10, because I'm actually calculating 4 values in there. And these registers get reused after 4 blocks. So there's a lot of complicated ways of doing that. Generating code here for this one is not that trivial. But the idea is basically you get to the steady state and you keep running forever in a very tight steady state, and then you ramp up, steady state, and ramp down. So this basically gives us a close to optimal use of resources. And in here, like if you look at what happens in here, you get now you can get 2 cycles per iteration. So you start from 9 cycles, single loop, you unroll it twice, get to 8 cycles, and then actually did some transformations, get to 4.5 cycles. And now if you do software pipeline, you basically shout everything down to 2 cycles.
I think there's a problem with, can you go back? Yeah, this one. If you look at the first iteration through, there's 2 BGE instructions at the end, but in your section of 2, there's only 1 BGE instruction in there.
I think what happened was, I think there has to be a BGE in here. I think that's what happened. See?
Yeah.
So I had to move this block. I moved this block a little bit too early. So if I go here, move this block. Will I get it? Yeah. Yeah. Good catch. Because I didn't start I start steady state a little bit too early. I didn't wait till the real steady state happened. Now in here that you actually get the BG in here. Good catch. So okay. Okay. The thing about this is you need a lot of registers. So that is why actually we cannot really do software pipeline in x86. Like Itanium has 128 registers. It's really set up to do software pipelining, because you every iteration you keep because you have to keep copies of values in there. And also there are issues of dependencies. We assume that I can just shove multiple iterations next to each other. How about if next iteration uses the data produced in the current iteration? For example, right now there was one, I equals I plus 4 was, each iteration was dependent. Of course, we got rid of it by doing I equals I plus 16 and having 4 different variables. But how about if you can't do that? There could be real things that the dependence, you can't really do that. And at that point, you have a lot of other things happen. And also the worst thing is all the loads and stores for multiple iterations now happen out of order. Okay, that means have you proven that they can actually do that? So if you don't know whether I am actually, there are some dependence, you can't actually. So there are a lot of things that can restrict this from happening. And there are a lot of code generation issues, because thing is right now you kind of doing this round robin things. You are in one iteration you are using one register value. Next one you have to pass it to the next one. You kind of have to pass them round, and you have to kind of pass the values round in some kind of round robin fashion. So in fact, some of the modern architectures has this concept of rotating registers. So what that means in the first iteration, I use R1, R2, R3, because otherwise you can't name it nicely. And the next register iteration, when you say R1, you actually got R2, and when you actually refer to R2, you actually got R3. So you actually registers get rotated on you, and it keeps rotating down there. So at that point, you can actually have very tight encoding instead of really having a very complex unrolled encoding, because otherwise in order to have rotating register you actually have to unroll the loop 4 times and then do all those crazy things. So something like Itanium, if you look at Itanium, it provides a lot of facilities to do software pipelining. So that's how a machine like Itanium really gets its speed. Okay, so that's kind of right now. If you go to a state of the art conference, there will be a bunch of talks on software pipelining issues. That's kind of the state of the art in there. Still, there are a lot of cool stuff going on in that. So next I want to touch on issue, and then I will just leave it as a problem because there's not really a good solution, which is register allocation and instruction scheduling. So you have a choice. You want to register allocation before instruction scheduling. And if you do register allocation before instruction scheduling, you have to choose. You have already chosen registers. What that means is there's limited number of registers and you can move things around, because normally in your intermediate representative you have infinite registers. So that means if you have two different things with the infinite registers in the temporary value, you can move them around. But the minute you allocate same register to that thing, you can't move them around. So you basically restrict the thing. So here's a good example. So here's what see what happens. So what happens is I move something into RAX, and I add RAX into RBX, and then I move something else again into RAX, and I add that into RCX. So I use RAX as a temporary twice. So if you look at this graph, I get a dependence graph like this. The real dependency is basically actually 1 to 2 there's a real true dependence, and 3 to 4 there's a true dependence, because I load it and use it. Everything else is a false anti-output dependence. Okay, do you see that? Okay, so you get a schedule like this. Okay, nothing much can happen because everything has to go sequentially. But what you realize is all these things are there because I use the same variable. I have a big anti-dependence in here. How about if we just use a different register like we did before? And suddenly all these dependencies vanished, and voila, I get a much tighter schedule. So in some sense, scheduling before register allocation makes sense, because I have infinite registers, I haven't even given something, so every time I know there's a different value, I give it a different register, and great, I don't get this anti-dependence effect. I can actually do a lot of things. So what happens if you do register allocation before, instruction scheduling before register? So after you do instruction schedule, you have this beautiful, nice, tight schedule, and you go register allocate, and you say, oops, you don't have enough registers, you have to spill. And you have all this very tight schedule, you just have now you're just inserting this ugly spill code in between. And so you're running very tightly and done. There's 5 instructions to spill. Very tightly, okay, so you got rid of this beautifully done thing. And you're changing the whole schedule for worse. So that doesn't help either. So if you look at right now, there will be enough papers today that people haven't come up with a good solution to this, because both of them are very hard problems. Okay, solving, I'm going to talk about register allocation next time. Solving each problem is there in P-complete problems, very difficult formulation. Solving it by itself is hard enough. Combining both just makes it completely unwieldy. So nobody has a way of combining both. So everybody has heuristics. So yeah, if you do that, why don't you run scheduling again and back and forth? Still, there's no good thing in here. So the final thing I want to talk to you about is hardware versus compiler. So you have this beautiful, most state-of-the-art hardware out there called this AMD 64 chip. It basically does many interesting things. It do out-of-order execution. So what that means is, if an instruction stalls, it will go and try to go from the instruction stream and find something that's supposed to come afterwards and run it before that. It actually does that in hardware. So all the things we are doing in scheduling, it's trying to do it in hardware. And there's a good thing about it, because what it does is it can tolerate unpredictable latency. So assume I keep doing something, and suddenly I had a cache miss. And suddenly that entire thing that depended on that just gets come to screeching halt. And instead of waiting, you can say, okay, wait a minute, are there anything behind it that actually is not depending on that I can bring forward and run? So it does that. The bad problem is hardware scheduling is, since you are doing hardware, you can't look beyond certain amount of instructions. You have an instruction window of a few hundred instructions. You can reorder things around that. But if you're doing compilers, you can look for other iterations. You can go, because you have compile time, you have a lot more freedom to do movement. So this provides some benefit of scheduling, but not everything. So what that means is scheduling for x86 64 is not that important, because hardware will actually do a good enough job for you. So it won't probably give you that much of a benefit of doing that. So another thing hardware does is register rename. So the thing that what happens is if there's anti-dependency. So assume I have register in there, and I am waiting to write it. I'm waiting to read that, and somebody else wants to write to the same register. And right now, normally what happens is, oops, there's interdependence, I just have to wait. But in modern hardware has a difference between virtual register and physical registers. They have much more physical register. They said, okay, wait a minute, I know it's the same same register that you give, same exposed register, register that you have, that you named is RAX, but I can actually give it two different registers internally, and then basically let somebody else actually load, and I keep tab of all this renaming inside in hardware. So they can do that. But it cannot do this complex transformation like what we did for this program, like saying, okay, yeah, this I equals I plus 4, and I can actually do I equals I plus 8 and j equals j plus 8. That type of transformations it can't do, because it's a lot more complicated, you need a lot more analysis. For simple renaming it might do, but hard things, so still the compiler is important. So, so the key thing is, in superscalar, is hardware and compiler scheduling works hand in hand. One thing hardware can do is it can easily reduce the burden when it's not predictable by the compiler. So if you have, for example, if you have memory lock reference, you might not know whether you get a cache hit or a miss. You probably will schedule assuming it's a cache hit. But in the case of cache miss, hardware will help you around in that. And compiler can still enhance performance by looking at much larger regions and priming hardware in a way that it has a lot of things it can access. And especially when you have actually hardware that doesn't have this kind of superscalar, that doesn't do renaming and stuff like that, things like the Itanium machines or DSP, this scheduling becomes a lot more important. So the good news for you guys is still things like scheduling is very important for Itanium. The bad news is, because hardware is doing also part of it, it's very hard to understand and figure out implications of things you do. Okay, because the hardware is complicated. The second thing is Intel is not, and AMD is not even publishing all the algorithms they do. Okay, so inside this black box there are things that happen. Okay, so if the black box does it, you don't really have to do the compiler. You have to figure out the things that black box doesn't do and get the compiler to do it for you. And so because of that, if you say, I am going to rename registers, you spend all this time rename, and you run and say, wait a minute, there's no difference. Because the hardware is doing that for you, and you don't know that. So that's what it makes optimizing for this box harder. So that goes into the next thing I was going to talk about. So one thing we were going to do for this next project segment is we gave you one of things to do, register allocation. We had to do register allocation in the segment. But then we'll open the floor to you. So what Punya is going to do is he's going to supply with 2 or 3 or 4 loop lists. Okay, few nice loops. That will be probably something very close to that will happen in the program that we go for the Derby. Okay, so it's your mission is to figure out how to run those loops faster. Okay, so instead of saying write these 3 or 4 optimizations, you can go and figure out, okay, what can you do to get that loops run faster? Okay, and people can go crazy on that, and I don't restrict. Only thing restrictions I would say is you better explain why what you did was general. So somebody came up with the idea saying, wait a minute, if there's no input for some benchmark, I'm going to go partially evaluate everything and compile the program down to 5 printf statements. That might not be, it would be hard to kind of explain that that could be general technique. So instead of saying, look, I found this thing that has a function, another thing, somebody says it is a rand function, I can actually do random function. I found this random function, I know what happened, I actually generated this data. So you have to be creative trying to explain. I mean, I'll tell you some people in the compiler community has gone to very creative distances. For example, because a lot of times, at least in good old days, people bought machines for how fast the machines ran. So there was this, you get a new architecture and how fast the machine ran was very important. So the way you measure that is by using benchmarks. Say for this benchmark suite, I have a number which is faster than your machine. So getting benchmarks fast was very important. So this one group realizes this one benchmark has this optimization, which most of the time you can't do it because you cannot really prove that it's correct. But for that benchmark, it worked. So they said, Dan, I want to do that for that benchmark only, but I can't do it anywhere else. So how do you do that? So somebody said, wait a minute, that benchmark has the comment that says written by Jack Dongara. I said, I will check for that comment, and if there's a comment appears saying written by Jack Dongara, I will turn on that optimization and apply it there. So everybody's trying to figure out how did this program run this fast? And there's no way you can prove that. They can figure out output code and figure out, okay, yeah, this running that thing, but how can you prove that this transformation can be done, because it's very hard. So they're trying to figure out, did they do something amazing? And somebody just by accident realized if you actually eliminate that comment, that optimization didn't happen. And so they realized so they actually did something really sneaky. And then these days people have a lot more in these communities that do benchmarking, have a lot of rules saying you can't do things like that. So I don't want that kind of things, but actually Punya gave some hints what kind of things you can do. So for example, one thing to follow is really good use somebody else's hints. So GCC probably has a really good compiler, or Intel compiler is really good compiler. So one thing you can do is say, okay, wait a minute, if I have a loopness, if I write it in C and write it in GCC, what would they generate? They are smart. They have spent more than a week or more than 2 days. You guys are trying to come up with the code and say, okay, wait a minute. So what does that? So some code they generate might be very weird to read, and you can try to understand and say, okay, how did they get there? And that might give you hints for different things what to do. So just go with a little bit of exploration and try to figure out a few things and do that. And then we give you that freedom in this one. So it's something people spend lifetimes doing. These kind of things, but see how much you can push within few weeks. And what we really like to know is in your submission to explain what you went about, how did you select that optimization. So you'll get points for doing the optimization, but you'll get also points for saying, okay, this is my process of selecting this to be a good optimization. And the best, if you actually figure out and did some good things, you can actually probably get good results in the Derby. So for Derby, what we are going to do is 12 hours before we will release the piece of code. So this is a very tricky thing. Beforehand, we used to release it at the Derby, before the Derby gets started. Problem that is, a lot of people's compilers are so finicky, they can't get all the optimizations working. And half the class basically because these compilers are written in few days and it doesn't work on new code. So if you release 3 days before, you will be writing a compiler that's going to, at the end of the day, produce going to be 3 printf statements, and that will only work for that program. We don't want that either. So we want to be able to do something in the middle. So we'll release it 12 hours in advance, so you'll have enough time to debug your compiler, but hopefully not enough time to come and do something very specific new optimizations for that to get that fast. So, and also the other thing is, if you win the Derby, you have to explain to Punya what optimization you did. You can't say, okay, I figured it out, I know the answer, and I just looked at it and put some printf statements to get the answer. That doesn't work. Okay. With that, tomorrow we'll cover register allocation.